Welcome to the fascinating world of nanomotors, nanomachines, and nanorobots, where engineering meets the molecular scale. These are machines so small they operate at the scale of individual molecules, opening revolutionary possibilities in medicine, manufacturing, and technology. First, let's understand just how incredibly small we're talking about. So how small is a nanometer exactly? 1 nanometer equals 10 to the negative 9th meters, or 1 billionth of a meter. That's a decimal point, followed by 8 zeros and a 1. To put this in perspective, a human hair is about 100,000 nanometers wide, a red blood cell is 10,000 nanometers, and DNA is just 2 nanometers across. Let's do a quick calculation to visualize this scale. If we scale up 1 nanometer to equal 1 meter, then a person who is 1.7 meters tall would be 1.7 billion nanometers. At this scale, a person would be 1,700 kilometers tall, stretching from New York to Florida. A nanomachine is to us as we are to planetary distances. That's how incredibly small these devices are. Now let's explore what nanomotors actually are and how they work. Nanomotors are devices that convert various forms of energy into mechanical motion at the nanometer scale. Imagine a tiny propeller that spins using chemical fuel, creating motion at the molecular level. Nanomotors can be powered by different energy sources. Chemical nanomotors use fuel molecules, like hydrogen peroxide, to generate motion through catalytic reactions. Light-driven nanomotors are powered by photons, converting light energy into mechanical movement. Magnetic nanomotors are controlled by external magnetic fields, allowing precise remote manipulation. Ultrasound nanomotors are activated by acoustic waves, useful for medical applications inside the body. Let's calculate how fast these tiny machines can actually move. Here's a back-of-envelope calculation for typical nanomotor speeds. A typical nanomotor moves at about 10 body lengths per second. If the nanomotor is about 200 nanometers in size, the actual speed equals 10 times 200 nanometers per second, which is 2,000 nanometers per second. That's 2 times 10 to the negative 6 meters per second, or 2 micrometers per second. Now you might ask, is this fast or slow? Let's scale this to human size, a 1.7 meter person moving at 10 body lengths per second. That equals 17 meters per second, or 61 kilometers per hour. Relatively speaking, nanomotors are incredibly fast, like a person sprinting at highway speeds. The physics at nanoscale is completely different from our everyday experience. What forces dominate at the nanoscale? In our world, gravity dominates, but in the nano world, surface forces like van der Waals forces and electrostatic interactions dominate. Let's calculate the Reynolds number, which tells us about fluid behavior. The Reynolds number equals density times velocity times length, divided by viscosity. For a nanomotor in water, Reynolds equals 1,000 times 2 times 10 to the negative 6 times 200 times 10 to the negative 9 divided by 0.001. This gives a Reynolds number of approximately 4 times 10 to the negative 7th. This is extremely low, meaning viscosity dominates completely at the nanoscale. Swimming at the nanoscale is like trying to swim through honey for us. Nanomachines are more complex devices, with multiple moving parts at the molecular level. Nanomachines are molecular assemblies with multiple components that work together, like tiny molecular factories. A perfect example is ATP synthase, nature's own nanomachine found in every living cell. ATP synthase is about 10 nanometers in size. It rotates at about 100 revolutions per second. Let's calculate the power output of this molecular motor. Each ATP molecule stores about 50 kilojoules per mole of energy. That's 50,000 divided by Avogadro's number, approximately 8 times 10 to the negative 20th joules per molecule, at a rate of about 100 ATP molecules per second. The power output is approximately 8 times 10 to the negative 18th watts. This is incredibly efficient for such a tiny machine. Scientists have created synthetic nanomachines inspired by nature. The 2016 Nobel Prize in Chemistry was awarded for the design and synthesis of molecular machines. Scientists created molecular rotors, switches, and even molecular cars, vehicles just 1 nanometer across. There are several types of synthetic nanomachines. Molecular rotors have components that spin like tiny wheels. Molecular switches can toggle between different states, like tiny on-off switches. Molecular elevators can move cargo up and down along molecular tracks. Nanorobots represent the next level programmable nanomachines with specific tasks. Nanorobots combine sensing, actuation, and computation at the nanoscale to perform specific program tasks. DNA origami robots use folded DNA strands to create programmable nanostructures. DNA robots are typically 50 to 100 nanometers in size. These robots can deliver drugs to specific cells, sense molecules in their environment, and even perform simple logic operations. The most exciting applications of nanorobots are in medicine. Imagine nanorobots that could seek out and destroy cancer cells while leaving healthy tissue untouched. Let's calculate how much drug a nanorobot could carry. A nanorobot with 100 nanometer sides has a volume of 10 to the negative 21 cubic meters. If 10% is cargo space, that's 10 to the negative 22 cubic meters. Assuming each drug molecule occupies 10 to the negative 27 cubic meters, that's about 100,000 molecules per nanorobot. With the trillion nanorobots, you could deliver 10 to the 17th drug molecules. That's approximately 0.1 micromoles of drug, delivered precisely where needed. Despite the promise, there are significant challenges to overcome. The main challenges include providing power to nanorobots, controlling them precisely, manufacturing them in large quantities, and ensuring they're safe for the human body. The power density challenge is particularly severe. Modern batteries have an energy density of about 1 megajoule per kilogram. A nanorobot has a mass of about 10 to the negative 18th kilograms. So the available energy is only about 10 to the negative 12th joules. At a power consumption of 10 to the negative 15 watts, that's only about 1,000 seconds of operation. The alternative is to use chemical fuel from the environment, like glucose in the bloodstream. Let's do some detailed energy calculations to understand feasibility. How much energy does it take to move a nanorobot through water? The drag force equals 6 pi times viscosity times radius times velocity from Stokes' law. Water viscosity is 0.001 Pascal seconds, for a radius of 100 nanometers and velocity of 2 micrometers per second. The drag force equals 6 pi times 0.001 times 10 to the negative 7th times 2 times 10 to the negative 6th. That gives approximately 4 times 10 to the negative 15th newtons. Power equals force times velocity, approximately 8 times 10 to the negative 21st watts. This power level is definitely achievable using chemical reactions or light energy. Manufacturing billions of identical nanorobots is another major challenge. There are several approaches being developed. Bottom-up approaches use molecular self-assembly, where molecules automatically arrange themselves into desired structures. Top-down approaches use nanolithography and etching, similar to computer chip manufacturing, but at smaller scales. Biological approaches use DNA origami and protein engineering to create programmable nanostructures. Let's estimate the cost per nanorobot. Materials cost about 10 to the negative 18th kilograms times $1,000 per kilogram for specialized molecules. That's about 10 to the negative 15th dollars per unit for materials. The main cost is fabrication and quality control, not the raw materials. Let's look at what's actually working in labs today. Today's working examples include chemical motors powered by hydrogen peroxide, magnetic microrobots for targeted delivery, DNA walkers that move along tracks, and light-driven nanomotors. Catalytic nanomotors are the most developed technology. They decompose hydrogen peroxide into water and oxygen gas. The oxygen bubbles provide propulsion, pushing the nanomotor forward. Speeds up to 100 body lengths per second have been achieved in laboratories. What could the future hold for nanomachine technology? Imagine swarms of coordinated nanorobots working together to repair tissue, clean arteries, or fight diseases. The potential applications are revolutionary. Targeted cancer therapy, where nanorobots deliver chemotherapy directly to tumors, minimizing side effects. Clearing arterial plaque to prevent heart attacks by removing blockages at the molecular level. Repairing damaged neurons in spinal cord injuries, potentially restoring movement. Environmental cleanup, where nanorobots break down pollutants and toxins at the molecular scale. When might these technologies become reality? Today we have simple lab demonstrations. By 2030, we might see first medical trials. 2040 could bring limited clinical use. Widespread therapeutic applications might arrive by 2050. With such powerful technology comes important ethical questions. What could potentially go wrong with nanorobot technology? Concerns include unintended biological effects, privacy issues from internal monitoring, and inequality in access to these advanced medical treatments. Safety protocols must be extremely rigorous before human trials begin. Let's summarize the key points about nanomotors, nanomachines, and nanorobots. Nanomachines operate at the 1 to 1,000 nanometer scale, billions of times smaller than everyday objects. Physics at the nanoscale is completely different, dominated by viscosity and surface forces rather than gravity. Current technology includes working catalytic motors and programmable DNA robots in laboratory settings. Medical applications have the potential to completely revolutionize healthcare and disease treatment. Major challenges remain in providing power, precise control, and mass manufacturing of these devices. Practical commercial and medical applications are likely still decades away, but progress is accelerating. This field beautifully combines physics, chemistry, biology, and engineering in ways never before possible.